So what I'm going to try to do now is hit present. If everyone, I think everyone's basically muted. So I'm going to go over and hit present and try to show you my screen. I'm still exploring different technologies for like drawing and scribbling on graphs. I think this is not the best solution, but hopefully it'll work for this week and we can do better next week. So the first thing I wanted to do was to do a quick review on, let's see, a quick review on MinCut, which we had talked about on Monday, although the video for that didn't turn out, and I'm going to have to try to re-record it. But MinCut is a bottleneck finding problem. So a cut in a graph is a cut in a graph is a set of edges. Ooh, that's not good. A cut in a graph is a little thicker. Yeah. So a cut in a graph is a set of edges where I remove them from the graph and they disconnect the source from the destination. So graph cuts are interesting for like logistics problems. If I'm trying to like ship goods and through a transportation network, and I want to know where the bottlenecks are, graph cuts are interesting with regards to like breaking the chain of like infection for an infectious disease. Graph cuts also come up in vulnerability analysis. If you're like making a communications network, you might be interested in what's the cheapest way that an enemy or an adversary or a denial of service attack could break connectivity between the source and the destination. So a graph cut is just any set of edges that breaks the connection between A and B. So once I take out these two edges, there is now no longer a path from A to B. This graph, we say that like the cost of a graph cut is the sum of the costs of the edges. So it costs 1 to cut this edge, it costs 2 to cut this edge. So this graph cut as a whole has a cost of 3. And we are often interested in finding the cheapest graph cut. What is the cheapest way to disconnect A from B? And so if one, either like myself or my enemy, wanted to break transmission or connectivity or communication between A and B, the cheapest way to do that would not be to cut the 1 and the 2, but instead to cut the 1 and the 1. Okay. So 1 and 1. I'm going to check the chat quickly. So this is a cut that has a cost of 2, which is cheaper than the previous cut, which had a cost of 3. I'm going to jump over quickly just to see if there's anything in the chat. And it looks like there's not. Okay. Questions on MinCut, or does this the problem here make sense? Check.
I just wanted to like confirm. So this is like MinCut is like a brute force kind of, so it's like really expensive. Like it's not actually a good idea if we have anywhere near a large number of edges possibly.
Yeah, so this gets what Courtney's asking about. I think this is Courtney, right?
Yeah, this is Courtney.
Okay. Sorry, I'm reasonably okay with voices, but yeah, so there's a question. The problem of MinCut is find the cheapest cut, and the question then is how we do that. And if we have a very large graph, then doing brute force and checking every different pair of edges or every different triple of edges and then every different set of 4 edges in a more complicated graph, you might have to break like 10 different edges in order to cut connectivity from A to B. Certainly from like an internet point of view, if you wanted to break internet connectivity between Los Angeles and New York, there's a ton of different fiber optic connections that zigzag across this country, and completely disconnecting LA from New York would require cutting a very large number of edges, and trying every possible cut to see which one was cheapest is not something that would be feasible. So I want to solve the min cut problem, but unfortunately, the only ways that I can think of to solve the min cut problem are really expensive. We also saw just very briefly that the obvious greedy algorithm of like erase the cheapest edge and then go and erase the next cheapest edge, that works fine here to just go and try erasing cheap edges first. But I asked you on the homework assignment to think about why there might be graphs where just checking out erasing cheap edges first was not going to allow you to quickly find the min cut on a more complicated graph. So, yeah. But I still would like to solve min cut. And it turns out that Dr. David Carger, whose class I had the pleasure of taking many years ago, he came up with a really clever algorithm for min cut. And, you know, you can Google for David Carger min cut if you're interested, but that algorithm, although it's brilliant, is beyond the scope of this class. And so I wanted to show you min cut because I think it's an excellent illustration of how sometimes the right algorithm for a problem like min cut is not obvious and requires us to think about solutions to other problems or other related problems. So my goal today is to introduce you to a related problem called max flow. And I'll do that in just a moment here. Let me go and pull up my max flow picture.